Right, got the M2 moments question, the old specification from 2004. It's old, but still, I like this question. So we've got this ladder, AB, mass M, length 2A, one end on rough horizontal ground. Coefficient of friction is 0.6. The other end of the ladder rests against a smooth vertical wall. A builder with mass 10M stands at the top of the ladder. To prevent the ladder from slipping, the builder's friend pushes the bottom of the ladder horizontally towards the wall with a force of magnitude P. This force acts in a direction perpendicular to the wall, because if he pushed it at an angle, his mate would fall. The ladder rests in equilibrium in a vertical plane perpendicular to the wall, next angle alpha with the horizontal. Very difficult to describe without being in the same room what that means, but it basically means that angle is alpha and it's not leaning over to the right or left. And tan alpha, it says, is 3/2. And we're going to show the reaction of the wall of the ladder is 7 mg. And find in terms of mg, the range of values of P for which the ladder remains in equilibrium. There's going to be a reaction from the floor, we'll call it RA, and from the wall, RB. Now, if the blow's not pushing very hard, the ladder's going to try and fall down, so the friction will be opposing that. But if he does push it quite hard, so the ladder's trying to go against the wall, the friction will be going in the other direction. So we don't really know whether it is, but it'll give us a range of values for P. Now, first part, I'll do moments about A to find out what this RB is, the reaction of the wall on the ladder. The RB, well, acts along this line, so I've got to do RB multiplied by this length, so it's really this length, which is 2A sine alpha. And the weight of the ladder acts on this line, so, and this side is A cos alpha, so it's mg times A cos alpha, and the same with the 10 mg, but it's 2A cos alpha, because the bloke at the top, his weight acts along this line, so we need to multiply by this length, which is 2A times the cos of alpha. I think the easy way to do this is divide by cos of alpha, because it tells us what tan alpha is, which means this, the A will go, and the sine alpha will become tan alpha. This one will just be mg, and this one will be 10 mg multiplied by 2, because we lose the A cos alpha. Tan alpha is 3/2, so this is RB multiplied by 3, and this is just 21 mg, so the RB is indeed 7 mg. And then it says, find in terms of m and g the range of values for P for which the ladder remains in equilibrium. And like I say, if the P is really big and pushing towards the wall, the friction is going to be going to the left, and if P is small, the friction is going to be helping it to stay where it is and going to be going to the right. But we're going to need to find out what the maximum value for the friction is first. So the RA, we can work out that's just 11 mg, just looking at the vertical forces. Now that means if we know what RA is, we know the coefficient of friction is, we know what the maximum value for the friction is going to be. That'll be mu times the R, which is 6.6 mg. So for the minimum value for P, the friction, as I say, is going to go into the right. So the friction, the maximum value for the friction plus the P, that's going to be just 7 mg, because that's the only force going to the left, the reaction at B, giving P is 0.4 mg. Now for the maximum value of P, the friction is going to be going to the left because P is really big now and the friction is opposing it, going to the left. And if we look at the horizontal forces again, we've got the P, which is going to the right, equals the friction, and the RB, which are going to the left. And that's 6.6 plus 7 mg, which is 13.6 mg, giving us a range of possible values of 0.4 mg to 13.6 mg.